So what we're going to do is we're going to take Heather's trip down to the core room. 44 seconds? Okay. How long, like, was she just sitting out there in the middle and you just kind of grabbed him and went?
She was at her desk.
She's at her desk, okay. So what I'm going to do is this. I'm going to say that Heather, we're going to graph Heather's velocity. So I'm going to say that the x-axis is time and the y-axis is v of t. And so when I first mentioned this to Heather, she was just sitting there, right? So her velocity was what? 0. So then I would say that when t is 0, her velocity would be 0, and they're going to graph her velocity. It looks something like that, right? So then I said, all right, Heather, let's go find Mrs. Spina, run down to the core room, and her velocity started to change from being 0. She got up, and she started moving, and so I would say that her velocity was positive there, right? And I would say that her velocity was positive because she was running out of the room, and so her distance from the room was increasing. Her position relative to the room was increasing. So I'd say her velocity was positive. And then somewhere in the hall, she, spotted the core room, and she started to slow down, right? Her speed started to decrease. We've done things like this before. And then when she arrives in the core room, I would say her velocity probably at least 1 point hit 0. Hi, Mrs. Spina, I'm here to pick something up. And I don't know, hopefully she did something like this. Maybe she stood there for 3 seconds. She just kind of stood there. Hey, I'm here to pick something up. She's not moving anymore. So I would say for that little interval, her velocity was 0 for those couple of seconds there. And then, of course, once she gets the stuff, she heads back towards the room. And so I would say her velocity then actually becomes negative. The reason why I would say her velocity is negative is because her position from the room starts to decrease. She's getting closer to the room. And so then she's running through the hall with this negative velocity. She's running back towards the room. And of course, then she spots our door. She starts to slow down. And she comes back into the room, goes to her seat, and now she's been sitting at her seat the rest of the time. Would that be a fair graph of her situation? Mm-hmm. Okay. So then the concept here, of course, is the net change theorem. And there's 2 concepts we're looking at here. One of them is displacement. And the other one we'll talk about here in a second is distance. So Heather's displacement for that little trip would be the integral from A to B. And we'll be specific here. I'm going to say for her, it would be the integral from 0 to 44 seconds, because that's what we timed her at. It took her 44 seconds of v of t dt. So if we wanted to do her full displacement for that whole trip, what would you say her displacement would be? 0. So we could do this one of 2 ways. We could look at this graph and make some inferences from the graph, or the easier way would be like, look at her and be like, well, she started off right there, and look where she is. Right there. Remember, displacement is only concerned about where did you start and where did you stop. That's all that really matters. And since she started in her chair and she stopped in her chair, her displacement would be 0. And so if I did look at these 2 areas, maybe you would agree that those 2 areas are equal size, but one of them is below the x-axis and the other one's above. How far do you think it is down in the core room? How many feet? What would you guys say? 50 feet? Is that fair? 50 feet? I don't know. I'm just making that up. Okay, so then if the distance to the core room was 50 feet, what kind of an integral could you set up where the answer is 50? Let's say the answer is 50. What's the question? What kind of an integral setup would that need to be?
What's the area she covered?
Like
going to?
No, it needs to be an integral. Like I'm looking for you to say the integral from somewhere to somewhere of something.
0 to 22.
0 to 22. I like it. Why'd you pick 22?
Is that about half the time?
We're going to assume she ran about the same speed, right? Going there and back. And so if we said, hey, the integral from 0 to 22, so let's say 22 is right there in the middle. The integral from 0 to 22 might be 50, we would say, right? Okay, so then if the answer was, so this was equal to 0. So if the answer was equals negative 50, what would have been the question? From 22 to 44, yeah. Integral from 22 to 44 of v of t, because her net change in location for the second half of the journey was negative because she came back. Does that make sense? And there will be all different types of integrals. Like if we knew how to figure out those areas, maybe analytically, maybe if we had a function for that, we could figure out other displacement, like pieces of the displacement as well. Okay, does that make sense for displacement? Okay, so here's the truth though. If all we said was, hey, Heather's displacement was 0, that tells part of the story, right? But it doesn't tell the whole story, because we all know what she did. She ran down the hall and she ran back. And so displacement tells a little bit of the story, but distance, total distance traveled, would tell the other half of the story. So the formula, or the setup for total distance traveled is right down here. It is the definite integral from a to b of the absolute value of v of t. So what does absolute value do to a number? Make sure that it's certainly not negative, right? It's either 0 or positive. And so if we look at Heather's graph again, but instead of graphing v of t, if we decided to graph absolute value of v of t, I would say that that would not change the first part at all. The first part would start at 0, it'd go up, it'd come down, it'd be right there. So it'd look exactly the same as the other graph, but wouldn't it take that negative part, the part where the velocity was negative, and reflect it above the t-axis? So that part would look like this. Okay, so we'd still be thinking about areas here. We know that we decided that this area was 50. We decided that that area was also 50. So if we decided to say the integral from 0 to 44 of the absolute value of Heather's velocity, what would you guys say the answer to that would be? 100, yeah. And so this actually tells a little more of the story, right? I mean, the displacement being 0 makes sense because she started in her seat and then she finished in her seat, so that tells part of it. But then the other part is she actually did run down the hall. Her total distance traveled was 100 feet. Because isn't the truth of the matter that while Heather had a 0 displacement during that time she went to get the candy, didn't you guys all have a 0 displacement too? Didn't you just sit there? And so that's why I say displacement tells one part of the story, total distance traveled tells another part of the story. Let me ask you this. In what circumstances would displacement and total distance traveled be the same number?
A one-way trip.
A one-way trip. If you never turned around, right? So if all Heather did was like run down to the core room and be like, sweet, Snickers, and she had a weak moment and she's like, well, I know what to do with these, and she just sits there and eats all of them, and then she just sits there in the core room for the rest of the day, I know we know she wouldn't do that, but if she did do that, then her displacement would have been 50, and her total distance traveled would have been 50, at least as far as we're concerned. So if she never turns around, they'd be the same. Okay, that makes sense? I hope that's a good illustration for you to try to remember those two formulas. A chance for you guys to practice these on the next page. So if you'd flip over and check out those two examples. I do direct you on that next page to use Math 9 to help you just maybe practice that again. So please do set up the integrals mentioned in the next, I think it's the next question, number 2. Yeah, number 2. So just do 2A and B for now. And we'll talk about 2C in a little bit. So ready, set, go with 2A and B. So for A, you've got to write this down. You've got to write down the integral from 1 to 5. And then you can write out the whole expression for v of t if you want. But the honest truth is, if all you really wanted to do was just write v of t dt, you are 100% welcome to do that. Does that make sense? Totally welcome to do that. And then down here, integral from 1 to 5 of absolute value of v of t. Once again, we know what v of t is. If you want to write it out, the whole thing, you're welcome to do that, or you can just leave it as that. Okay, so then as far as what you do with the calculator goes, I need to erase those so I can push the buttons on the calculator. But here's all you really need to do. You don't have to do this step. I am going to enter this into my y equals, just because I'm going to do this twice. So it's going to be minus 10x squared plus 29x minus 20. So I'm putting this into my y1. You don't have to do it this way if you don't want to. I kind of like this because we're going to do it twice. Here's what you do. You go second, quit, get out of there, and we're going to go math 9, integral from 1 to 5. And then instead of typing the entire rule for the function out in there, I'm just going to go, if you remember the keystrokes, it's alpha trace. And I put my velocity equation in there for y1. So it's going to be alpha trace, pick y1, hit dx. And did you guys get that answer? 10.6666, etc.? Okay. And then because I entered this into y1, the second one will be easy as well. So it'd be math 9, integral from 1 to 5. And this time I'm going to go math num 1. That gives me my absolute values. Then I'm going to go alpha trace to get back to my y1, and then dx on the end. So hopefully you can see the advantage, potentially, especially if you're going to do it more than once, of putting in your equation into the y1 or the y2 or whatever you choose. And then you hit enter, and we get something different, right? 11.8333. So the fact that displacement and total distance traveled are different numbers, what does that tell you about this object? What did it for sure do? It for sure turned around somewhere, at least once, right? Maybe more than once, but it for sure turned around at least one time. That's right. Okay, so then what do you have to do to write this down? So here's what I'm picturing. Maybe you can picture this with me. I'm looking at the left half of the screen like it's your quiz or your test or your final exam or whatever. You got this question right in front of you, and you got your calculator right beside you, right? What do I have to write down to get credit? I'm sure you know this. That's not going to get it done, right? Not going to get it done. That's the right answer. We can all see it. It's right there. Not the right answer. Or it is the right answer, but it's not going to get you the credit you want. What you need to do is write down your setup. Integral from 1 to 5 of v of t dt equals 10.667 feet or something like that. That's full credit. You're showing your setup. That tells me you know exactly what you're doing. And you got the right answer, which tells me you know how to do the details, whether you did them yourself or whether the calculator did them for you. On this one, I wouldn't care, right? Because the calculator is active. Yes, ma'am?
Do you care if we write v of t or if we actually write out like the t?
Either way. Either way is fine by me. I kind of like putting the v of t in there simply because it's faster. You can put whatever you want, though. Either one. Okay, and then for the other one, of course, you write the setup, and it'd be 11.833, so on, feet. Feeling comfortable? You're doing okay? Okay, awesome. The last one here, question C is a little bit different. I want you guys to try this one. This doesn't require the calculator because it says if a particle is at position x equals 4 when t equals 9, write an integral expression for the position of the particle when t equals 20. So all you're doing is you're writing an integral expression that if you did do math 9 or you did actually evaluate it, you'd get the answer. All I want you to do is simply set it up. Make sense? Just set it up. Don't worry about the details. Don't worry about math 9. Don't worry about doing any antiderivatives or anything. Just set up an integral expression. All right. Give you a few minutes to ponder that. We'll discuss in a second. 4 when t equals 9. So that's our starting point. So I'm going to say that my final position is going to be 4 plus my change in position. That make sense? So my final position is where I started plus how far I moved. Forwards or backwards. This particle is not changing. It's not doing two-dimensional or three-dimensional motion. It's just going back and forth. So I know that it started at 4, and I know that it moved, but I don't know how far and in which direction. Okay, so what would be a better way to write that? How do you find change in position? Say again? Okay, yeah, delta, so like delta position, definitely, but like think about what we're doing. We're looking for an integral expression. The integral of what? You said displacement. The integral of what? There you go. So what if I rewrote this as 4 plus some integral from somewhere to somewhere of velocity dt? Isn't the definite integral of velocity equal to the displacement? So the final piece here, and I'll get your question. The final piece would be, what kind of limits of integration? Like what would be the two numbers on my integral? 9 and 20. That's right. So it'd be 4 plus the integral from 9 to 20 of velocity would give me 4 plus my displacement, or you could say 4 plus my change in position. And that would give me my final position. Kind of like this, like the analogy I used yesterday. Like what if I emailed you tonight and I said, guys, you won't believe it. I grew 2 inches yesterday. Would you expect to show up and see a 2-inch tall teacher? What would you expect? Yeah, however tall I am right now, I'd be 2 inches taller. So you take my old height, kind of like my starting position, plus my change in height, that would give you my final height. Newsflash, I've already hit my final height. How it goes. Okay, Bailey, your question.
Why did you, I just added by 9 instead of 4. Is it just because you're adding the x?
You know what? It's just apples and oranges. 9 is a time. And if I asked you what my final position was, if I said, hey, I traveled 10 miles, and you said, well, what time did you start? That doesn't really matter. You would say, well, where did you start? So we need a location plus a change in location, not a time plus a change in location. Does that make sense?
Yeah.
Okay. Good question. Easily mixed up. Anything else? Okay, so we're going to build this out a little bit further. I think this is going to time out just about right. We're going to use Math 9 again on something. Will you guys look at this next example? It says, example where Math 9 is very useful. This also illustrates some good stuff about calculus. So read this over. It's a very briefly worded question. It says, find f of 5. So that's our goal. That's our end game. We're going to try to find f of 5. If f of 1 equals 3, and then they give you this f prime equals, oh, sorry, that should be root log x. Sorry, that's a typo. F prime of x equals root log x. There we go. Anyways, okay, so they want to know about f of 5. They've given you a little bit of information about f of 1, but then the next piece is about f prime. So I want to kind of guide you through this. We'll use Math 9. Let me ask you a question. I think this will help give us direction. If, it's going to be a broad statement. I think it's good, though. If you are asked about f, but they mostly gave you information about f prime, what are you going to have to do? You're going to have to do an antiderivative, right? And so here's what I would propose. I would say, you know what, let's do this. Let's say integral of root log x, right, because that's the integral of f prime, should give us information about f. And I'm going to put some limits of integration on this too. I'm going to say that one of my limits of integration should probably be a 1. What should the other limit of integration be? A 5. Let's talk about why. Why would I pick a 1 to be one of my limits?
Starting point.
It's my starting point. That's what I know about, right? I know that f of 1 equals 3. That's my beginning point for whatever's happening here. Why would I pick a 5 to be my other limit? That's what I want to know. I'm trying to find it. So I am going to, I think this is good. I'm going to write this. I want to rewrite this a little bit. It's not, I'm just going to write, I'm going to write it like this. We know that f prime of x is really root log of x. I get it. But what I want to do is I want to write this out to be a little more useful form for us. I'm going to write that this equals, first of all, what's the antiderivative of f prime? It's f. So I'm going to write f of x evaluated from 1 to 5. And then I'm going to expand this a little bit further. I'm going to write integral from 1 to 5 of f prime of x equals f of 5 minus f of 1. Does that also make sense? Now here's where this gets a little bit, here's where the connection happens, right? So we know that f of 1 is 3. And f of 5 is the thing that I'm trying to figure out. What on earth do I do with that left side? It's the integral from 1 to 5 of root log x dx. That's where math 9 comes into play, right? Root log x, no matter how far we go through the year, that's not going to be something that you're going to be able to handle. And so math 9 is super handy here. Can you see how this finishes? Don't we just use math 9 and then add 3 to both sides? And we'll have what we want. Okay, so this is basically, again, using the net change theorem, saying that our final value equals the original value plus the change. Final value equals original value or starting value plus change. So see if you can navigate math 9 real quick and then add 3. And once you've done that, we should have f of 5. Any proposed answers? 5 point what? 5.561. Okay. Sounds like you guys all agree with that. Any questions? Okay, fantastic. So let's take a peek at our last one here. I've got your quizzes I'm going to hand back to you here in just a second. Let's flip over to this next one. And I want to make a little connection for you. I want to kind of get you started. And let you kind of run with it, and I'll hand back your quizzes. Make sense? Okay, cool. So this the title here, Using the Graph of f prime to Help Find Absolute Extrema. And this, of course, is a pretty old term, right? It's been a little while since we looked at this. So let's talk about absolute extrema. Of course, absolute extrema means min and max. What are your candidates for absolute extrema? Endpoints are critical numbers. Yep, there you go. So candidates are endpoints and critical numbers. Okay, so what would the endpoints be? -7 and 8. Yep. Okay, so, whoops. I'm going to start my little table here. My x's and my y's. And I'm going to use -7, and I'll just put the 8 down there. Okay, critical points, you said. Critical points of f are where what is happening? Do you see any places where f prime is 0? -6 and 4, right? So these 3 places are where f prime is 0. So -6, -2, and 4. And of all my 5 candidates, I already know all that I need to know about one of them. Which one do I already know everything about? Yeah, f of -2 equals 3. It's right here. So that's kind of like my starting value. I know for sure that that's what's happening at f of -2. Okay, so then I've got 4 other candidates to deal with, right? So let me ask you a familiar question. If I'm looking for information about f, but all I really have is information about f prime, what am I going to have to do? Got to do an antiderivative, and specifically a definite integral. So I want to set one of these up for you, and then I'll let you guys run with the rest of them. My first target is going to be when x equals negative 7. Okay? So I'm going to say, I'm going to use an integral, as you mentioned. I'm going to say the integral from negative 7 to 2 of f prime of x dx. And I'm going to put a little equals over here in a second. Or sorry, negative 7 to negative 2. I was about to ask why did I pick those, and there would not have been a really good answer for why did I pick 2. Okay, so why would I pick negative 7 to be one of my limits? That's what I want. Why would I pick negative 2?
That's the known.
Yeah, the starting value or the known, yeah. Okay, so then the final piece here as far as the setup goes, what does that equal? What would be the symbolic answer on the right side?
F of negative 7.
Other way around.
F of negative 2 minus F of negative 7.
There you go. Does that make sense? So this should remind you a lot of the one we just did. The mechanics are going to be a little bit different. F of negative 2 is 3. We're still looking what f of negative 7 is. Here's the mechanics have a change. Math 9, not going to do you much good here. How on earth am I supposed to figure out the integral from negative 7 to negative 2? Areas. It's all piecewise linear. So all you're going to have is a bunch of triangles up there. You all know how to find the area of a triangle. Yes? And so I would start finding all those various areas up there. You can use the areas to help you calculate the definite integral. Yes? Okay. And then that should allow you then to find f of negative 7 pretty easily. So why don't you do that really quick? I'm going to hand out your quizzes to you. So that's, 1 by 3? And that's 4 by 4. That one is 6 by 2. This one is 4 by 2. So negative 7 to negative 2. Did you guys get 6.5 for that integral? 6.5. Of course, the 1.5 accumulates as negatives. Does that make sense? Because all those y values are below the x-axis. So negative 1.5 plus 8 would be 6.5. So then you subtract the 3, divide by a negative. I got negative 3.5 for f of negative 7. You guys agree with that? Okay. Okay, so then what comes after this? Basically the same thing. Same kind of strategy to be able to figure out the other candidates' values. So if I was going to try to figure out what's going on at negative 6, I would go integral from negative 6 to negative 2 of f prime. And that's equal to 3 minus f of negative 6. And then I can do that definite integral pretty easily because I have all my areas set up now. What would you guys say the integral from negative 6 to negative 2 would have to be?
Negative 5. No.
I don't think it's negative. Oh, you're looking at a final value. I'm just asking what the integral would be.
8.
8. There you go. So 8 equals this. And then I think, Audrey, your idea of negative 5 for f of 6. Right, you subtract the 3, divide by a negative. I think negative 5 makes sense. And then you just continue on, right? So you'd say integral from negative 2 to 4 of f prime. Notice how I'm taking care to make sure that my lower limit is actually the lower number. And that's equal to f of 4 minus 3. Once again, I know that f of negative 2 is 3. What would be my integral from negative 2 to 4? Negative 6, right? It's area of 6, but we're below the x-axis. So negative 6 equals f of 4 minus 3. You'd add the 3 over and you get negative 3 for that y value. And then the last one would be integral from negative 2 to 8 of f prime. That would equal f of 8 minus 3. It's very repetitious at this point, right? We're basically setting up the same sort of integral repeatedly. What about the integral from negative 2 to 8? It's negative 2. So negative 2 equals, oh, I'm in exactly the wrong spot. How about this? Negative 2 equals f of 8 minus 3. So you add 3 over and you get 1. So then your final steps here would be to point out what the min and the max are. You'd say the min is negative 5. Max is 3. What do you think? Questions? It's a pretty good place to kind of wrap it up there. Okay, so take a look at your quizzes. Wondering if you have any comments or concerns, questions, and